Now let's look at an interesting kind of collision problem. It's really not a collision, you treat it like a collision. It's always in the collision section of the book, right? So usually you're talking about a person on a frictionless sled or a barge or something that's free to move. And the person has a significant mass mp, and the barge, I'll call it a barge, has a significant mass mb, and this is frictionless. And since it's frictionless, the person and the barge are isolated. They make an isolated system because there's nothing that can apply any force lateral because the surface is frictionless. We'll say the barge has length L from 0 to L, right? And we'll see if we can figure out what's going to happen when a person walks from the end to the center of the barge. So they're going to walk to L over 2. What's going to happen? So first let's test our intuition with the demo. So here is my frictionless barge. It's on wheels. I've bolted a couple of the carts together. Pretty frictionless. It's 0 to L long. And first I just want to test our intuition. What's it going to do when I walk on it? So let me push it over this way. And then I got to jump up here. All right, so I will be the person, and this is the barge. And I'm going to stand on the edge, and I'll walk a little more than halfway, just so you can really see the barge move. So as I walk forward, the barge moves backwards. Whoops, a little bit of friction there. So let's now calculate what we expected to happen. So we're going to calculate how far does the barge move back? That's really the question. All right, so to do that, we would be helped to have sort of an initial and a final state. So allow me to erase my frictionless word here, because we can use this as our initial positions of everything. So on the x-axis, I was at the origin, the edge of the barge is at the origin, the barge is L long. And what's going to happen is we're going to walk a little bit, and we just saw that the barge gets pushed back. I walked, let's say, to L over 2. Of course, the origin isn't here anymore. It moved back. So what we're trying to calculate is this minus s, the shift backwards, where this is the origin. I'm at L over 2. So how much did it shift back? That's the question. All right, so the way you can think of this as a collision is the idea that I collided with a barge. We had an interaction with each other, yet our center of mass doesn't move because we are an isolated system. So all we got to do is calculate the center of mass before and the center of mass after and set them equal to each other, and that should tell us the answer. All right, so let's look at the initial x center of mass, right? So the center of mass is 1 over the total mass times the position of each mass times where it is, right? So 1 over mp plus mb, right, times my position times my mass, but I'm at 0, so that's nice. So that's m of the person times 0, plus now we got to do the barge. Well, if we assume its mass is uniformly distributed, we can think of it as a rod, and we know its center of mass is at the center, and we know as isolated object itself, it acts like all its mass is at the center. So this would be mb times L over 2. If we treat it as a point particle, it's at L over 2. That's the initial. Now let's look at the final, where everything is shifted around. Final center of mass. Where is it? Let's see how we want to write that. Again, it's 1 over the total. 1 over mp plus mb. And now it's my position times my mass times my position plus the center of the barge times its position. So my position is what? I walked forward, I walked to the middle, right? This distance is L over 2, but I'm not at L over 2. I'm at L over 2 minus s because it moved back. So it's mass of the person times L over 2 minus x. I'm sorry, minus s. That's how far I got. Okay. Plus the contribution of the barge. And let's see, the center of the barge is there. So it is also L over 2 minus s. Yes, I forgot. If I walk to the center, then our masses are at the same place. So mb times L over 2 minus s. Right, okay. I really should start reading these notes ahead of time. All right, so now what we're going to do is equate these two. All right, let's equate this equals to this. So the first thing we can do is cancel the common terms. So we would cancel that and that. Total mass doesn't matter. And then we would say, oh, well, that's 0. So we have mb times L over 2 equals mp times L over 2 minus s plus mb times L over 2 minus s. Right? And then, I don't know, we could see that probably the quickest thing to see is that mb L over 2 is over here and mb L over 2 is right there. So that one cancels, right, if we're doing our algebra tricks. And then we're down to just mp times L over 2 minus mp times s plus, or minus mb times s equals 0. So we could solve this. What are we solving for? We're solving for s. Okay, let's solve this for s. So we would say minus mp times s minus mb times s. So we would bring those over here, and it would be mp plus mb over here, and s over here. Yet we still have this one mp times L over 2, which we'll have to bring over here, minus mp. I've algebraed myself here. Okay, let's solve this now. Are we ready? We're solving this for s. Let's say this is equal to 0 is equal to mp times L over 2 plus mp plus mb times minus s. Let's do that and bring that over here and then divide and solve for s. Thank you. And what you get is mp over mp plus mb times L over 2. So that is how far it shifts. It depends on the ratios of our masses. And we can check this sort of with common sense. What if I weighed essentially nothing compared to the barge, right? If I weigh nothing compared to the barge, then what's going to happen? The barge isn't going to care that I walk to the middle. It's going to have very little effect. If it was me and like an aircraft carrier, the shift is going to be nothing. And sure enough, if I weigh nothing compared to the barge, this is basically 0. So the shift is essentially nothing. What if I weigh a lot more than the barge? What if it's me and a knee board? Somehow I can balance on a knee board and I were to walk, then the barge would respond a lot, right? The barge would really want to move back. And sure enough, if my mass is biggest, this is basically 1, almost 1. And in that case, yeah, the barge would move back to where I would pretty much stay in the same place. But the maximum you could ever get is L over 2, because I only walked to the point L over 2. So the answer makes sense. Another kind of question we can ask with these problems is, let's see, if the person walks at VP, how fast does the barge move? And if we think back to the previous demo, we saw the barge move back. So you could consider some sort of average velocity. If I had been walking smoothly, the barge would have moved smoothly. So let's calculate how fast the barge should have moved. So one thing about these is these are tricky, because this is a little bit of an imprecisely asked question, is these involve what frame of reference you're talking about. So when you say the person walked at velocity VP, you got to be specific. Do you mean with respect to the barge or with respect to the lab frame? Because the barge is moving, right? So usually when I think of these questions, if they say the person walked at VP on the barge, that's their impression of how fast they walked on the barge. Therefore, it's in the barge frame. But if you're watching the barge move back and ask how far does the barge move back, well, that's probably in the lab frame, right? So hopefully if you have a question like this, it'll be real specific, or you'll just have to interpret it. So to make ours specific, how fast does a barge move? And I'll put with respect to lab. And I'll say a person walks at VP with respect to barge. And that should have us covered. Okay? So first, let's think about our sort of reference frames here and remember how we relate these things. We want to know the speed of the person in the lab frame, say. So velocity of the person in the lab frame. Remember, you just say it's the velocity of the person in some frame plus the velocity of that thing in the lab frame. So that's the barge. The person in the barge frame and the velocity of the barge in the lab frame. So if you write it like that, it'll always come out right. But this isn't what we're going to use to solve the problem. We need this, but we also need to remember this is a collision of bodies in an isolated system. Therefore, the center of mass does not move. So we want to say the velocity of the center of mass is 0. But we have to get that center of mass in a specific reference frame. We can say we could do it in the barge frame, we could do it in the lab frame. Right? Let's do it in the lab frame. That usually makes a little bit more sense to do. So let's do that in the lab frame. Then all we got to do is say the velocity of the center of mass is 1 over the total mass, person plus mass of the barge, just like before. And again, we just weight each velocity with the mass. We say it's the mass of the person times the person's velocity in the lab frame, which is VPB, the velocity of the person in the barge frame, plus the velocity of the barge in the lab frame. Right? And then we also need to consider the barge's velocity plus MB times the velocity of the barge in the lab frame. Right. There's your two terms. There's your center of mass. And what's it equal to? 0. The center of mass is not going to move. Right? Now let's see if my algebra skills have increased here. So what were we asked for? We were asked how fast does the barge move with respect to the lab? Oh, okay, we're trying to solve for this. Trying to solve for that. Okay. Equal to 0, so I can cancel that. Multiply both sides by the total mass. And now we're solving for the velocity of the barge in the lab frame. So what would I do? I've got MP, MP, MB, MB. MP, I would bring these, take that one to the other side and divide by the total mass. So I'm going to get a negative. And this is the part I didn't take over. MP over the sum, MP and MB I did take over, P plus MB times the velocity of the person in the barge frame. And that's actually what you were given in the problem. And just like the position, we can now check, does this make sense? Let's see, if the person is really light, if you're walking on an aircraft carrier, then basically the barge's recoil velocity, it will be negative, it should be, right? We know that the barge moves backwards, but it'll be really small. If this is my mass and that's an aircraft carrier, then essentially nothing. Or if I'm heavy walking on a light barge, then it will move back at about the same speed. And that's kind of what you'd expect. If this is the biggest number, then this is basically -1, and it moves back. So again, think of it as a collision, make the center of mass not move, but also this one, when you get into velocities, requires a little bit of reference framework. Let's look at rocket propulsion again and think of it in terms of momentum. So we talked about it before. You may recall we showed a bottle rocket flying across the amphitheater before, and we talked about how a rocket, this is really the only way a rocket can move in space, because it has nothing to push against. There's nothing to push with friction like when you walk. So all it can do is be loaded with fuel, ignite the fuel, shoot the fuel out the back, and we have to conserve momentum. So if we have fuel coming out the back, let's imagine a little bit of fuel moving with velocity VE and saying it has a mass, this little chunk of fuel has a mass delta little m. That's flying out the back. You must conserve momentum, so the spaceship must pick up a momentum going the other way. And that's really how the rocket moves. So if you think about it, the velocity of the center of the mass, the velocity of the center of mass of the system is 0. And the system actually doesn't go anywhere if you consider the center of mass of the system. It just stays right here. But a lot of the fuel goes this way, therefore the rocket goes that way. calculations of the kinematics are complicated because the rocket's mass is changing. You can't just say it's a force acting on a mass m. Big M is going down as it expends the fuel. So that's what makes this a little complicated. But we can solve it just by saying delta P of the system has to be equal to 0. If that's the case, then delta P of the fuel, and when I say the fuel, I mean the fuel that's getting kicked out. The fuel that's in the rocket is still considered part of the rocket. The fuel flying out plus delta P of the rocket also has to equal 0. So let's think. In this process where a little bit of fuel comes out at the exhaust velocity and you get a little bit of a kick to the rocket, let's write down these two changes in momentum. See, for the fuel, it must be negative because we're going to say this is the positive direction. So minus delta M times VE, minus delta M times the exhaust velocity. And this one must be big M times the increase in the rocket's velocity. Right. And those two together must equal 0. So we want to do two things with this equation to be able to work with it. We want to switch to differentials. So let's go from delta to d. Right, and then, okay, well, that's easy. We could say minus dm, that little change, VE plus m, dv of the rocket equals 0. That wasn't a big change. But there's another change. There's another substitution we can make. And we want to get it all in terms of sort of one set of differentials, right? We have dm of the fuel and we have big M of the rocket. But there's a relationship between those. If some fuel gets kicked out dm, that same mass must have been lost by the rocket. Right? So we have this relationship that d little m equals negative d big M, because there's conservation of mass. If mass comes out of here, dm comes out of here, it must have been lost there. So what we can do is rewrite this equation and just substitute that right there. And we can say dm times VE times the exhaust velocity plus m times dvr equals 0. And now this is getting down to an equation that we can actually integrate and solve. Right? So what we're going to do is get all our derivatives on the other side of each other. So let's get dvr by itself. Right? This is the one we really want to know, is how fast is it going to go. dvr equals minus, and what will we end up with? VE on the other side, m over dm. dm over m. There we go. Right. And now we just do this trick where we integrate both sides between some limits, right? So there we go. And we're integrating from, say, VI to VF. I'll give up the big R as a subscript. And the mass is going to go from some initial mass to some final mass, some change in mass. All right, so integral of dVr is just VR. All right, so we apply that, the final rocket velocity minus the initial rocket velocity, R final minus R initial. And then the integral of that is the natural log of the mass. Remember, the mass is a function in time. The mass is changing. Right. So minus VE times the natural log of the final mass over the initial mass, if you remember how to do that. Right. Natural log of m evaluated from MF minus MI. And what we see that's really as far as we need to take that. This is what we need to know, is how much of a change in velocity you have for the rocket. The increase in speed depends on several things. So if you want the rocket to go fast, either to get somewhere fast or to escape the gravity well of the Earth, equivalently it needs to go fast, you want a large exhaust velocity, clearly. So the faster that exhaust blows out the back, the faster your rocket will go, and that's why there are big chemical explosions. The other thing is you want a large MF to MI ratio. No, let's switch it, make that positive. We do want the rocket to go forward, right? So that negative sign can switch, and then you flip this over. That's what a natural log will do for you. There you go. So you want a large mass initial to mass final ratio, right? So what that means is you want mostly fuel. You want most of the mass to be fuel. Because if most of the mass is fuel, then you have a very large initial mass, and by the time you've blown it all out, you have a very small final mass. This is why rockets carry so much fuel to go fast and to get out of the Earth's grip. The other useful thing you can calculate from all these equations somewhere is you can get the thrust. Let's see, which one of these is going to get the thrust? It was big M times delta V equals this, right? What if we took a time derivative of this? This would be big N times dV dt, ma, right? So that's ma, so this must be the force, right? So the force of the thrust you get from taking the time derivative of this, ma equals the exhaust velocity times dm dt. So the faster you burn the exhaust, or the faster you burn the fuel, the bigger your thrust. None of these results are surprising. These all make sense. You expect all these things to be true. But to get it, you got to think a little bit about a system where a mass changes. And that's fairly unusual. This is one of the main places that it comes up.